Hello everyone, welcome to IIT-JAM in Chemistry tutorial number 40, and this is part 2 of lecture number 2 of the physical chemistry chapter solid state. The points lattice vectors and crystal directions were discussed in the first part of lecture number 2, where the subtopic was elementary applications of vectors to the crystal systems. Now in the second part of lecture number 2, two new points are going to be discussed, and these are Miller indices and reciprocal lattices under the same subtopic. So the third point is Miller indices. We already have had some idea about the Miller indices. These are generally calculated by using the normal vectors. So what is a normal vector? It is nothing but the vector that is perpendicular to any crystal plane. Now let us see the stepwise calculations regarding how to obtain the HKL values of a lattice plane. First of all, we have to find out the normal vector of the normal vector to the plane, followed by calculating the intercepts of this vector with the crystal axis, and finally we have to reciprocate these values, followed by clearing the fractions in order to obtain the Miller indices. So let us elaborate this process with an example. So this is a unit cell. Okay, two unit cells are adjacent here, and the lattice plane cuts the A axis at 3/2 distance, the B axis at half distance, and the C axis at unit distance. Okay, so the intercepts are 3/2 along A axis, that means 3/2 A, this is half B, and this is C simply. Now the reciprocal of 3/2 is 2/3, half is 2, and 1 is 1. After clearing the fractions, we get the values. Just multiply with 3. So 2/3 into 3 means 2, 2 into 3 means 6, and 1 into 3 means 3. So 263. Therefore the Miller index of this plane is 263. Now few examples of some important lattice planes such as 100, 110, and 111 planes of the 4 space lattices. The interplanar distances of these planes with respect to the edge length A for a cubic particularly are also discussed here. So here this is a 100 plane, this is a 100 plane. So this is a set of 100 planes for a primitive cubic lattice. This is a 110 plane, this is a 110 plane, this is a 111 plane, this is 111 plane. So this is a set of 111 planes for a cubic lattice. Okay, now what about the interplanar distances? The interplanar distance, that is denoted as D, and in the suffix the Miller index of the plane. Okay, so this is D100. What is the value? Now this is, they are A distance apart. Okay, so this is A, and there is a formula. There is a formula of this thing, that is A divided by root over h square plus k square plus l squared. So this way it has been calculated. Okay, so A divided by root over 1 squared plus 0 squared plus 0 squared, that means it is A. This is A by root 2. They are A by root 2 distance apart. So D110 is A by root 2. Similarly D111 is A by root 3. For a face-centered cubic lattice, the corresponding distances of the lattice planes for 200 planes, that means this is actually 100 plane, but in forming the lattice planes we have to follow some rules. That is, all the atoms or the lattice points must be covered, they should be parallel, and they should be equidistant. So this, in this regard, the 100 planes becomes 200 planes. Similarly these 110 planes become 220 planes. So this way face-centered cubic 200, 220, 111. Okay, for body-centered cubic 100 becomes 200, but 110 remains 110. On the other hand, 111 becomes 222. For a C-face-centered, 100 becomes 200, but 110 remains 110, and 111 also remains 111. So the corresponding interplanar distances are all calculated here. Okay, so look, have a look, and finally their ratios. So this ratio, if you can see here, this ratio is A is to A by root 2 is to A by root 3. Okay, so after clearing all these things, we get the value 1 is to 0.0707 is to 0.577. So this is the D100 is to D110 is to D111 ratio for a simple cubic lattice. Okay, so these data are very important when you will be analyzing the crystal lattice structures by X-ray diffraction method. Okay, so just have a look. All the 4 lattice planes have different ratios of the interplanar distance for correspondingly for 100, 110 and 111 planes. Okay, now reciprocal lattice. Okay, so the real lattice vectors A, B and C, they define the crystal lattice. Okay, whereas the reciprocal lattice vectors A star, B star, C star, these can be defined as A star, it is twice pi B cross C over A dot B cross C. You know the significance of cross vector and dot vector, cross product and dot product, isn't it? B star is twice pi C cross A over B dot C cross A. This way the C vector, reciprocal C vector, is also defined. So the reciprocal lattice is constructed by translating the reciprocal lattice vectors A star, B star, C star that exist in the reciprocal space, and it is related to the real space by a Fourier transform. By constructing the reciprocal lattice using vectors, what we can do? Number 1, we can describe the periodicity of the crystal in reciprocal space. Number 2, we can analyze the scattering of waves such as X-rays or electrons by the crystal. And finally, number 3, we can understand the crystal's electronic and vibrational properties. So that's all about today's lecture. Now let's solve one question here, and this is question number 4 of this chapter. So what is the reciprocal lattice vectors A star, B star, C star, how it is defined? So you are given 4 options, and just you have learned that this option is the correct option. Okay, so the correct answer is option B. So that's all about the part 2 of lecture number 2 of solid state. Thank you and have a nice day.